So, hello students. In this video, I'll be trying exclusively to talk about the classical harmonic oscillator, and then move on to the mathematical treatment of the quantum harmonic oscillator, and we better understand what an ideal harmonic oscillator is. It oscillates, and it has a periodic oscillation linked with it. And since I'll be precisely talking about the mathematical treatment here, that we exonerate on the treatment of classical harmonic oscillator, and then extend this description using quantum mechanical treatment to the same harmonic oscillator. Now, to start with, what we have is Newton's second law of motion, and this is the fundamental law of classical mechanics. And if I consider that we have a mass m, and this mass is attached to some spring, and this spring has a constant, what's called as spring constant, and that constant is small k, and the force is exerted by the spring. And this force that's exerted by the spring is given by Hooke's law. This force is given by Hooke's law, and we better understand that within certain limits, this force is directly proportional to the negative of the displacement of the spring, and we have F equal to minus kx, where F refers to the force. It will be more precise to call it the restoring force of this oscillator, and this x is it's a representative of the displacement, of the spring with respect to its equilibrium position. Now, we can think of can use it as 1, and we can think of Newton's second law of motion as F is mass times acceleration, and this a is the acceleration, this m is the mass of this spring, and we can equate these two equations, F is equal to minus kx and F is equal to ma. In doing so, what we can do is we can use for F here as ma is equal to minus kx. Now, the quantity that we have here, which is acceleration, now this acceleration is defined as the double derivative of displacement. So d2x by dt2, it gives us the measure of the instantaneous acceleration. And we can use the value of this acceleration into this equation, and we can obtain a second order differential equation from here. So this is m times d2x by dt2 is equal to minus kx, and we can rearrange the terms. So this is d2x by dt2 plus k by m times x is equal to 0. So what we have a second order differential equation, and from this equation what we have to do is to identify the angular frequency. So we can easily identify the angular frequency as omega square, and this omega square is equal to k by m. So the term that we have in this differential equation, which is k by m, this term represents angular frequency. I mean, it represents the square of the angular frequency. So we can think of writing omega square equal to k by m. And we can boil down this differential equation to d2x by dt2 plus omega square x is equal to 0. So what we have is we have a second order differential equation, and this equation has a general solution, and we can write down the general solution of this differential equation as x of t equals a cos omega t plus b sine omega t, where this A and B, they are the constants, and these constants can be determined by using the initial conditions of the problem. I mean, the initial conditions like the initial velocity or the initial position of the harmonic oscillator. Now, what we have procured here is that we talked about Newton's second law of motion, and what we did initially, we set up the equation for Newton's second law of motion, like F is equal to ma, and then we replaced this F that's here by the restoring force of this spring, and m is the mass of the oscillator, and a is the acceleration. And then we started with the Hooke's law, and what we did, we applied Hooke's law as F is equal to minus kx, where this k is the spring constant, and this x is basically the displacement from the mean position of this harmonic oscillator. And then what we obtained is we obtained a differential equation. And when we combined these two equations, we obtained a linear homogeneous second-order differential equation. And and solving this equation leads to the general solution of this harmonic oscillator problem. And the omega that's over here, this omega is nothing but omega is under root of k by m. This k is the spring constant, and m is the mass of the spring. Now, the solution that we have written down here, this solution x of t equal to a cos omega t plus b sine omega t, what it does basically, it's made of sines and cosines. So it's explicitly understood that it's describing the oscillatory motion of this mass that's hanging on, and around its equilibrium position, with respect to some equilibrium position, this spring is oscillating. It is oscillating with the displacement x of t with time, and this oscillatory motion is due to the restoring force of this spring. And then we have the constants. We have the constants that we have introduced in the solution of this problem, and these constants, constant A, constant B, they are to be calculated. They are to be determined by the initial conditions of the system, like the initial displacement, say x of 0, and the initial velocity, say v of 0. So to conclude this lecture on the classical harmonical oscillator, what we did here is we subjected the analytical derivation of this harmonic oscillator equation, and what it does basically, it provides a clear understanding of how the motion of the mass spring system is described mathematically, and highlighting the interplay between the force acting on the mass and its resulting oscillatory motion. So from here, we would like to move on to what's called as we will go with same analytical treatment of the quantum harmonic oscillator. So we would like to describe the same problem using quantum mechanics, and we would like to procure the difference, and would like to explicitly see the solution of Schrödinger's time-dependent wave equation that's exaggerated in the quantum mechanical treatment of this harmonic oscillator. And to start with, when we talk about the quantum mechanical treatment of harmonic oscillator, we start with Hamiltonian. And Hamiltonian, this Hamiltonian is it's a subject of kinetic energy and potential energy of an ideal system. So if we have to write down the Hamiltonian operator for an ideal harmonic oscillator, it will be P cap by 2m square plus 1/2 of m omega square x cap square. So this is my Hamiltonian operator for the harmonic oscillator. And this P is called the momentum operator. Call it momentum operator, and this p cap is given by minus IH cross d by dx. The next thing that we have here is x cap. Now x cap is it's the position, and this position is acting as an operator here. This x cap, which is basically x, this is called as position operator. Position operator. M refers to the mass of the oscillator, and omega is it's the angular frequency of the oscillator, and h cross that we have used here in the momentum operator, this h cross is called as reduced Planck's constant, because this h cross is h by 2 pi. Now, so this is our Hamiltonian for this oscillator, and if we write down the time-dependent Schrodinger's equation for this quantum harmonic oscillator, so that will be h cap of psi of x is equal to E psi of x. And this is our Schrodinger's time-dependent wave equation. Sorry, time-independent wave equation, and this psi of x that we have here is it's a representative of wave function, and E that's here. This is what's called as energy eigenvalue. Energy eigenvalue. I mean, the energy eigenvalue that's associated with the state that's described by this wave function. Now we have Hamiltonian, and we can substitute this Hamiltonian operator that we have written down over here. We can substitute this in time-independent Schrodinger's wave equation. So if we substitute for this Hamiltonian operator, what we will write here is minus h cross square by 2m d2 by dx2 plus 1/2 of m omega square x square times psi of x gives us E psi of x. Now let's try to introduce to make our problem simple, so that we can easily reach out to some solution of this problem. What we do is we introduce some dimensionless variables. So what we do is we introduce dimensionless variables, and what we do here, let's assume that we have some zeta, and this zeta is under root of m omega by h cross of x. All right, and when we make use of zeta equal to under root of m omega by h cross times x, so what it does basically, we can substitute this, and we can take its we can take its derivative with respect to x, and this equation is modified using zeta equal to under root of m omega by h cross x. So this can be done. You have to do the simple differentiations, simple algebra, and what you will do is you will obtain the differential equation as d2 by d zeta 2 psi of some zeta, then plus zeta square minus, say, k times psi of zeta equal to 0, where this k is 2e by h cross omega. Now we have a second order differential equation here, and we look for the solution of this second order differential equation. And this differential equation that we have here, it has the known solution. We know its solution, and we know its solution in terms of Hermite polynomials. We know its solution in terms of Hermite polynomials. And the symbol for the Hermite polynomial is Hn as the function of this zeta. So we can write down the wave function, And we can write down the solution for this differential equation as psi n of zeta is nn dot hn of zeta dot e to the power of minus zeta square by 2. And talking about the various parameters that we have introduced here, this n of n is it's called as normalization constant, and this hn of zeta that we have here, this is called as harmonic polynomial. And n that we have here, this n refers to the integral numbers starting from 0, 1, 2, and so on and so forth. This n is basically the representative of the quantum numbers that are corresponding to different energy levels of this harmonic oscillator. Then the next part of this harmonic oscillator is it's the energy eigenvalues. And in this case, I mean, the energy eigenvalues, that is En, of the quantum harmonic oscillator, they are quantized, and they are given by En equal to h cross omega times n plus 1 by 2, where this n is 0, 1, 2, and so on and so forth. So this is quantum numbers that correspond to the energy levels. And we can take on from here, say for example, let's take a couple of examples. I mean, let's talk about the ground state of harmonic oscillator. And for ground state, this n certainly is equal to 0. So in that case, En is going to be h cross omega by 2. And what we observe here, we have the energy at n equal to 0, and that energy is h cross omega by 2, and we call this energy as 0-point energy. And we can write down the ground state wave function also. So what will be that? That will be psi 0 of x is equal to n0 e to the power of minus m omega by 2h cross x squared. So all what we have done here is we have used the value of zeta here. So this is our wave function for the ground state of this quantum harmonic oscillator. And this n0, we better understand that the value of this n0 can be calculated by using the condition of normalization. And what is the condition of normalization? It is you can normalize this wave function from minus infinity to infinity, psi 0 of x. Take its square dx equal to 1. So using the condition of normalization, we can calculate the value of this n0. Then if we can think of moving a little bit further for the first excited state. Now if we talk about the first excited state, and for first excited state, n is equal to 1, and we can calculate here E1, and this E1 will be 3h cross omega by 2. And we can calculate the wave function psi 1 of x, that will be n1, then h1 times under root of m omega by h cross x e to the power of minus m omega by 2h cross x squared. And what is this h1? This h1 of zeta that we have here, this h1 of zeta is nothing but twice zeta for the first Hermite polynomial. Now, what we have here is we have the wave function. We have the wave function psi n of x, and what that wave function does basically, psi n of x that we have here, this wave function, it basically describes the spatial distribution of quantum harmonic oscillator in terms of the probability amplitude. And then we have En, what we call as energy eigenvalues. This En is these are quantized energy levels that this oscillator can have, each associated with some specific wave function. So you have an oscillator and you have the specific energies associated with this harmonic oscillator. Not only the energies are there, we are able to calculate the specific wave functions for this harmonic oscillator, like psi 0 of x, psi 1 of x, psi 2 of x, and so on and so forth. And the if we talk about this, what we call as the ground state energy, for n is equal to 0, we have seen that, of course, we have the lowest possible energy of this harmonic oscillator, which is called as 0-point energy. And then the potential term, that we have here is 1 by 2 m omega square x square. What it does basically, it confines the oscillator and leads to the quantization of the energy levels. It's this potential term that becomes the tool of quantization for the given problem. So what we have tried here is we have subjected the analytical treatment of the quantum harmonic oscillator, and what it does basically is it involves the solving the Schrodinger's equation with some specific harmonic oscillator, and this leads to quantization of energy levels and the derivation of wave function using the Hermite polynomials, which are the solutions to the differential equation that are arising from Schrodinger's equation. And I can say that the physical interpretation includes understanding this energy quantization and the probabilistic nature of the quantum states that are described by the wave function, which is not the case when we talked about the classical harmonic oscillator, where we have the solution of the second order differential equation in terms of its displacement, and the solution is oscillatory in nature, and there is classical continuity of energy that's linked with the classical harmonic oscillator. But that's not the case when we treat the same problem using quantum mechanical approach, and quantum mechanics has a different story to tell about this quantum mechanical harmonic oscillator, and which ends with two important formulations. One is the energy of the harmonic oscillator is quantized, and the next important thing is that at absolute zero, the energy of the harmonic oscillator is not equal to 0. It has some minimum energy, and that minimum energy is known as 0-point energy. Bye.